So, welcome everyone to lecture number 14 on Statistical Theory for Deep Learning. I would like to start with a remark concerning the oral exams for this lecture. I sent you already half an hour ago a Moodle message concerning this. This remarks concern all people who want to make an exam for this course as an advanced course. So all people who want to use this course as an elective course will have a written exam. The written exam is already scheduled for this summer for July 17th, and there will another written exam for those who missed this exam in next spring. But for those who want to make or want to use this course as an advanced course, they need an oral exam. And this oral exam will be about two courses. The second course is the mathematical statistics. The mathematical statistics was offered in the past only in German. So at the moment, if you do not speak German, you cannot make this oral exam for an advanced course. The mathematical statistics will be presented again in next year in spring. So after that you can make it as an advanced course, advanced exam, but not at the moment. So and because of this I will explain the whole thing only in German, because that's easier. Okay. Gut, also es geht um die Vertiefungsprüfung in der mathematischen Statistik. Da wird geprüft die mathematische Statistik zusammen mit der Deep Learning. Sprache ist dann Deutsch oder Englisch. Prüfung wird basieren auf den Prüfungsfragen zu beiden Vorlesungen, wobei ich dann die entsprechenden Prüfungsfragen zufällig auswählen werde, die drankommen. Also ich habe einen Zufallsmechanismus, um zu vermeiden, dass ich irgendwie da einen gewissen Bias reinbringe beim Auswahl. Dass ich sage, okay, der Student ist aber mir sympathisch, da will ich besonders nette Fragen, oder der Student ist mir unsympathisch, da will ich besonders unnette Fragen. Wird das also auch noch im Zufallsprinzip gemacht. Die Fragen werden Ihnen dann mehr oder weniger wörtlich gestellt. Also es kann sein, dass ich sie geringfügig modifiziere, um zu vermeiden. Oder auch, dann werde ich pro Antwort in der Regel noch einmal nachfragen, um zu vermeiden, dass Sie auf die Liste der Prüfungsfragen oder Liste der Prüfungsantworten reagiert haben und Sie haben nur auswendig gelernte Prüfungsantworten verstanden und sonst nichts. Also das möchte ich damit ausschließen. Okay, die Prüfung ist mündlich, die Dauer ist 35 Minuten. Circa, also beziehungsweise mindestens 35 Minuten, aber normalerweise mache ich dann genau 35 Minuten. Wird so sein, dass Sie sich aussuchen können, Sie können sich eine Frage zu Beginn aussuchen aus den beiden Listen der Prüfungsfragen, und damit legen Sie natürlich dann auch fest, ob Sie mit mathematischer Statistik oder Deep Learning anfangen. In dem Gebiet machen wir weiter, und da können Sie bis zu 5 Minuten drüber reden, ohne dass ich Sie groß unterbreche, weil das ist so für den Einstieg. Dann breche ich aber unter Umständen, oder meistens breche ich ab, es sei denn, Sie haben die Frage so geschickt gewählt, dass ich gesagt habe, das will ich aber jetzt unbedingt noch mehr hören oder so. Dann kann auch sein, Sie reden weiter drin, aber meistens breche ich dann ab, und dann haben wir zweimal 15 Minuten, wo ich mit zufällig ausgewählten Fragen aus beiden Gebieten ankomme. Es kann mal sein, dass Sie sagen, das passiert ab und zu schon, dass jemand sagt, okay, ausgerechnet diese Frage hat er jetzt nicht gelernt. Dann hat es natürlich keinen Sinn, wir diskutieren über die Frage, wo er gar nichts weiß. Dann kann ich eine neue Frage wählen. Das bedeutet aber automatisch eine Note Abzug. Und wenn es dann nochmal vorkommt, dann sind Sie automatisch durchgefallen. Das kam auch schon, also es ist mir auch schon passiert bei Vertiefungsprüfungen, dass Leute durchgefallen sind. Sie haben es dann aber in der Nachprüfung auch immer noch mit. Also es hat dann auch keine Auswirkung auf die Note der Nachprüfung. Sie haben dann bei der Nachprüfung nochmal das volle Notenspektrum. In der Regel machen die dann eigentlich auch in der Nachprüfung eine sehr gute Note. Und zumindest gut plus oder sowas, ne? Klappt meistens schon. Bonus gibt es auch, ne? Können wir sagen, der wird ja angerechnet. Also den Bonus können Sie haben in mathematischer Statistik, in Deep Learning oder in beiden. Und dann würde ich halt also am Ende, wenn ich mir überlege, was die Note ist, würde ich halt je nach Bonus, den Sie haben, ich mache 2 Teilnoten, die beiden Teilnoten eventuell noch um 0,3 anwenden und dann erst Mittel. Gut, das wollte ich eigentlich alles gar nicht erzählen, sondern was ich Ihnen eigentlich erzählen wollte, wir brauchen jetzt Termine, weil es sind ja mündliche Prüfungen, und ich mache die Terminvergabe jetzt so, dass ich erstmal eine Umfrage gestartet habe. Da habe ich Ihnen mal 15 mögliche Termine zwischen 16. Juli und 4. Oktober vorgeschlagen als Prüfungstermine. Wobei nach dem 16. Juli kommt eine Lücke und vor dem 4. Oktober ist auch eine Lücke. Die Haupttermine sind zwischen Ende Juli und Mitte September und Anfang August ist auch nochmal, oder Mitte August ist auch nochmal eine Lücke von einer Woche, also 10 Tagen oder sowas. Und da würde ich Sie jetzt einfach bitten, die Umfrage bis nächsten Mittwoch auszufüllen und anzugeben, welchen Termin bevorzugen Sie. Also es gibt, glaube ich, so bei diesen Terminumfragen immer 3 Sachen, so einen grünen Haken, so einen eingeschränkten Haken oder geht nicht. Ne? Und dann setzen Sie halt grünen Haken bei den Terminen, die Sie wirklich haben wollen. Können Sie auch mehrere machen, wenn es Ihnen egal ist. Und den eingeschränkten Haken noch möglichst bei denen, die irgendwie noch gehen. Und das, was ganz klar nicht geht, setzen Sie halt das Rote hin. Und dann werde ich versuchen, die Termine so auszuwählen, also wahrscheinlich, ich weiß nicht, kommt es darauf an, wie viel die Prüfungen machen werden. Ich nehme an, es werden keine 30 sein. Ich würde pro Tag wahrscheinlich 4 Prüfungen machen. Das heißt, wenn ich 10 Tage auswähle, hätte ich 40 oder so. Das heißt, ich werde auf alle Fälle mehr machen, als ich Antwort habe. Also mehr Tage anbieten, wo Sie eine Antwort bekommen. Aber ich werde auch gleich schon eine vorläufige Zuteilung machen, wo ich Ihnen einen Tag reserviere. Und dann haben Sie eine Woche Zeit, sich für diesen Tag anzumelden oder auch für einen anderen Tag, der noch frei ist. Also Sie müssen dann nicht diesen Tag nehmen, aber Sie kriegen einen vorgeschlagen, der eine gewisse Zeit, wahrscheinlich eine Woche, für Sie reserviert bleibt. Da schicke ich dann nochmal eine Nachricht rum. Oder Sie können sich auch gar nicht anmelden, auch eine Möglichkeit. Und irgendwann das später mit mir machen. Man muss es jetzt nicht in diesem Sommer machen, ich bin ja auch im nächsten Semester noch da, nächstes Semester. Das heißt, Sie können auch die Prüfung problemlos erst später machen. Okay, sind Fragen soweit zur Prüfung? Also Ihre Aufgabe wäre jetzt bis nächsten Mittwoch, diese Umfrage auszufüllen, wenn Sie einen mündlichen Prüfungstermin vereinbaren wollen. Dann haben Sie die Chance, dass Sie einen von Ihnen bevorzugten Prüfungstermin bekommen. Also ich werde es so machen, dass möglichst alle den Termin auch bekommen, wo Sie so einen grünen Haken hingesetzt haben. Kann natürlich sein, dass also wenn Sie zu wenig grüne Haken hinsetzen, kann sein, dass ich eventuell auch noch auf so einen zweiten ausweichen muss, aber nach Möglichkeit nicht. Gut. That was that announcement. Then we go back to English and I start with a repetition of the last lecture. What did we do? I explained something about packing numbers. We had definition 3.2. We had an epsilon greater 0. You have a calligraphic G, which is a set of functions G from RL to R. You had a P greater or equal than 1. You had a probability measure mu on RL, and you define the LP mu norm of G in the usual way. It's a LP norm where you integrate with respect to the measure mu. Then a finite set of functions G1 to Gn, and G is called an epsilon packing with respect to this norm. If the norm of the difference between any two functions is greater or equal than epsilon, so if they are more than epsilon or at least epsilon away in this norm, then the epsilon packing number is the minimal size of an epsilon packing, might be infinity in case that there is no finite packing, and the LP epsilon packing number of G on Z1n, points Z1n, that's the LP epsilon packing number of G with respect to the LP norm where you integrate with respect to the empirical distribution of Z1 to Zn. And then we have seen this packing number is related to the covering number because the packing number with radius 2 epsilon is less equal than the covering number with radius epsilon, and this in turn is less equal to the packing number with radius epsilon. Then we had the second definition, definition 3.3. Here you have a set of subsets of Rd, calligraphic A, and you have a natural number. Then SA and an endpoint set, Z1 to Zn, that's the cardinality of all sets of the form A intersected with Z1 to Zn. So that's the number of sets which can be subsets of Z1 to Zn, which can be picked out by the set of sets calligraphic A, where you define a subset can be picked out if it can be represented in the form one set of this A of this set calligraphic A intersected with Z1 to Zn. And then we say A shatters a finite set G, subset of Rd, if the shadow coefficient of SAG is equal to 2 to the power cardinality of G. So if every subset of G can be picked out by calligraphic A, and we define the n shadow coefficient of A as SAN, that's the maximum over all Z1 to Zn in Rd, such that SA and the set Z1 to Zn of these endpoints, or that's the maximum of this quantity. So that's the maximum number of different subsets of endpoints that can be picked out by. And if you don't understand it completely, it doesn't matter. This is Wapnick-Jabonek theory. Sorry guys, that's the usual thing. You can think about these things for long and you will also be a little bit confused. But that's normal. Okay, and one point here, and next I will present what we will do is I will present upper bounds on the, that's great. Maybe forget about this. Just turn it off. I will present upper bounds on the n shadow coefficient as a function of n, and that will be a measure of the complexity of this Z calligraphic A. And with this measure of complexity, I will also use this measure of complexity to bound the complexity of a set of functions, as you will see later on. But before we do this, I will introduce a quantity related to the shadow coefficient, and that's the VC dimension of VC stands for Wapnick-Jabonenkis of this set calligraphic R of subsets of Rd. And the crucial observation behind this definition is the following simple fact. If A, so that's our set of subsets of Rd, shatters or does not shatter, shatter a set G, subset of Rd. This means you have some subset of G which cannot be represented in the form G intersected with some set of A. Then it also does not shatter any set which has G as subset, superset. In A, it's also not shatter in G prime. With the probability, with the property that G is a subset of G prime, is a subset of Rd. Because you have because you have a subset of G, which you cannot represent in this form A cap G, and then you can extend this set, or you can just consider this set and this cannot be represented in the form A intersected with G prime. And this implies if we have the case shadow coefficient is less than 2 over k, which exactly means that there is some k point z which is not shattered by calligraphic A. Then also for all n greater k, if we look at the n's shadow coefficient of A, then this can also not be shattered. Is this clear? Yeah. Because we have this maximum in addition, does it hurt us? Yeah, I think I have to argue in a different way around. If this is, it's by contraposition. If this is 2 to the power n, then this will be 2 to the power k. That what follows from the line above. That's what you see. Okay, questions? But this means now that if you look at SAN as a function of n, then it will be for some time equal to 2 to the power n, and then starting at some times it will be less than 2 to the power n, all the times. And the first point, or the largest number where it's equal to 2 to the power n, that's the VC dimension. That's what I define in definition 3.4. Let A be a class of subset of RD. Which is not an empty class. Then we define the Wagner-Cherenkis dimension with notation VA, and that's the supremum over all n and n. So that S a n equal to n. This quantity is the so-called VC dimension of A. Or in words, this VC dimension is the largest number of points which can be shattered by A. Now I will look at the examples which we had in the last lecture. We first look at the set of all half-open intervals in one dimension. So the set of all intervals minus infinity to a, where a is an R. What is the Wapnick-Javonenkis dimension? So how many points can be shattered? What's the largest number of points which can be shattered?
Well, we said last time that it can shatter any 1 point.
It can shatter any 1 point set?
And it cannot shatter any two sets of points.
Cannot shatter any set which contains 2 points. So the VC dimension will be?
1.
1. Clear, yeah? First point. And it can shatter any 1 point set because you can, if you have 1 point, you can either make this interval end before this point or go above this point. And then you get this empty set or the complete set. And it cannot shatter 2 points because it fails to pick out the just or exactly the figure of the 2 points. Then our second example which we had was the set of all intervals from AB. What is the Wapnick-Javonenkis dimension here? It's 2, because this can shatter any 2 sets but not 3 sets. Now I could ask about the set of all half planes in R2, but we don't do this because we had some example, but we don't see. So we see what is shattered, but we don't see what is not shattered. So that's more complicated. Instead, I make see the fourth example. I look at the set of all convex sets. Of D, A convex. What is the Wapnick-Javonenkis dimension here?
I think it should be infinity because we
It should be infinity because
any
correct.
point today.
Because we have seen that we can shatter any n-point set. Just not any n-point set, but there are for any n there are n-points which we can be shattered here. It's a different thing. Because you can put these n-points on a circle and then you make. Or here, I think I make it with R2 here. But now on RD, it's also clear you make these endpoints on the sphere. Okay. Notes on the border of the ball. Okay, and now comes the thing I'm interested in. What I would like to prove today. It's a theorem from Wapnick-Javonenkis from the year 1971. Rather old. Let A be a subset of RD. Be a subset of. Be a set of subsets of. Be a set subsets of RD. With VC dimension. Then we have for all n in n. The nth shatter coefficient of A is less equal than the sum I equals 0 to dimension of A of n atop I. And if you look at the right-hand side, then you see immediately this right-hand side is a polynomial. It's a polynomial with this degree with dimension of A. So if you have a finite with dimension, then the nth shadow coefficient grows as n as a polynomial. And if this with dimension is infinite, then by the definition you have SA n is equal to 2 to the power n. Okay, you have a question?
Yeah, I just wanted to ask in examples, if we had calligraphic A being just one element.
Yes, if you have calligraphic A just being, so calligraphic A and the element is a set, is one set, yeah? Then you want to ask how many points you can shadow? Well, then of course these numbers of set which you pick out will be upper bounded by 1. So you can not shadow even 1. Yeah?
Meaning it would be 0.
Meaning it would be the supremum of the empty set, yeah. Not clear what I make. It's not clear. Yeah. Because I think we haven't defined, well, you're correct. It's not well defined here. Yeah? It would be minus infinity, which makes no sense here, formally, because this is the empty set. But it also makes no sense if I add here the 0, because I haven't defined what SA0 is here. But the meaning should be clear. But good point. Other questions? Okay, now we are in a typical situation in a math lecture. We have a theory, we need a proof. And I think I told you already several times about the idiotic behavior of young men, which results in higher premiums for insurance, against life insurance, for instance, for young men, because you have a higher death risk. But there's also an idiotic behavior of a little bit older men, or a little bit older math professors, which try to prove theorem 3.4 without looking in the lecture note, which is a totally stupid idea. Yes, oh, we will see. But this is some of, okay. Years ago I read about a guy who needs some challenge in life, and then he walked on, no, it wasn't walking, I don't know the English word for it, to the South Pole or North Pole, or something like this here, as the first one of the first people. And of course you can do such a thing, or you can also prove the experiments. Okay. Okay, so let's start. The first obvious observation is, without loss of generality, I assume that the Wapnicher extinction is less than infinity. Because if it's infinity, then I have an infinite sum, and if I define the binomial coefficient properly, so that n over I is equal to 0, if I is greater than n, then it is well-defined sum. And then you see this. You have here basically the sum of I equals 0 to n over I, which is just 1 plus 1 with exponent n by the binomial theorem, which is 2 to the power n. So then this will be 2 to the power n for all n, and then this assertion is trivial. So without loss of generality, because otherwise the right hand side is equal to 2 to the power n for all, and then the assertion is trivial. Now I have a finite VC dimension. I have to somehow use this information in my proof that the VC dimension is finite. We remember the definition of the VC dimension. It means that the A does not shatter any set of cardinality BC dimension plus 1. So I look at all, well, because what we show, Z1, Zn be in RD. And for arbitrary points, but we fix them at the moment, we show that the number of sets we picked out from this, which is A intersected with Z1 to Zn, A in calligraphic A, this number of Z is less than what we need. So I show this and then we are finished. Because the shadow coefficient is the maximum of this guy with respect to Z1 to Zn. And I show this way. Okay, now I have fixed points. I know that A by definition of VA does not shatter any set of cardinality VA plus 1. So I look at all subsets of Z1 to Zn. F1 to Fk be all subsets of cardinality plus 1. So the number of the subsets, and without a lot of generality, I can assume that is Z1 to Zn are all distinct, is n over VA plus 1, which is not interesting. We don't need for the simple, but I write it anyhow. Now I know that A, calligraphic A, does not shatter any of this by definition of VA of the sets. Cardinality of Fn equal VA plus 1. A does not shatter Fa for all RA. Which means that for each of these Fa, I can find some subset such that for any set A in calligraphic A intersected with Fa is not equal to this subset. Therefore, for each there exists HA, the subset of FA, such that if I consider FA intersected with A, that's not equal to HA for all A in calligraphy. Okay? now look at FA intersected to A. I claim this is the same as FA intersected with A intersected with Z1 to Zn. Can anyone tell me why this is the case? Please?
Fi is already a subset of Z1 to Zn.
Because Fi is a subset of Z1 to Zn. Yeah? So you see that these three sets, I can first make an intersection of Fi with this set, which gives Fi, and then I get Fi. It's clear. So maybe I mark it here. Since Fi is a subset of Zn by definition. And therefore, I can reformulate this set of sets which I have. A intersected with Z1 to Zn. Okay. This set of set is a subset of the sets of all well, it's obviously a subset of Z1 to Zn. I call this set C. And these sets have this property that Fi intersected with C is not equal to Hi for all I in 1 to K. Correct? Correct. So I call this set calligraphic C0. And then you see I have a superset of my original set. I want to show my original set has cardinality less equal than this guy, so it suffices to show that my superset has cardinality less equal than this guy. So it suffices to show that the cardinality of C0 is less equal to sum and that's what I will show in the sequence. And now the first observation is, in some special case, this is trivial. This is trivial in case that Hi is each time equal to Fi. Is trivial in case Hi equal to Fi for all. Why? Because in this case you have that A intersected with Z1 to Zn intersected with any of the Fi's is not equal to Fi. And the Fi are all subsets of cardinality VA plus 1. And you see what this implies?
The shadow coefficient is smaller
Than our sum, yeah, but why? The shadow coefficient is smaller than our sum, that's correct, but why?
because it's smaller than L0.
Because it's smaller than
L0 I thought.
C0, C0?
C0.
Yeah, but why is the cardinality of C0 then less equal than this guy? So we are now in the special case that let me write it down. Because then we have that Fi intersected with H is not equal to Fi. For all I. And what do you know then about the set in the red brackets? Please?
It is certainly not Fi, so it is
It's certainly not Fi, yeah, right?
any subset of Fi. Discrete subset.
Yeah, and what? Yeah, that's true. But how does this help us to bound the cardinality of it? We want to bound the cardinality. How many of these sets do exist? Yeah, that's the.
We can just calculate this by looking at how many subsets there are. Right? So
Yes.
we can
Well,
take
and maybe
any subsets of some
okay.
Fi.
But sorry, I was a little bit. I was a little bit. I should use C here at that point, yeah, because I'm talking about this set. Sorry for that, guys. I should use C here. That would be better. I was a little bit confusing here. Starts already. And that we have for all C in C0. And then I want to say something about properties of the set of C0. And this property is,
So if we look at the set C0, then this consists of all the sets C subset of Z1 to Zn, such that this intersection Fi intersect C is not Fi again.
yes,
This means C has to, it's not allowed to contain every element in Fi, but at least one element is not in C for any C. Otherwise it would be,
yeah, but how does this help you to bound the cardinality?
then we can just pick out I elements out of Z1 to Zn, and I is not allowed to be VA plus 1, because then we would be able to pick out exactly Fi, but if we just take less,
Exactly, because these are all subsets of cardinality VA plus 1. Then the C cannot have cardinality VA plus 1. So the C's are subsets of Z1 to Zn, but they must have cardinality less than VA plus 1. That's so all C in C0 must have less equal than VA plus 1. And of course this C was a subset of Z1 to Zn. Now you can count how many subsets of cardinality really strict small than VN plus 1 do you have? And well, you just count how many subsets do you have of cardinality I, where I runs from 1 to VA, and the subset of cardinality I, the number is n. I. And we are done. So in a special case we are done, and now the remainder of the proof is to reduce the general case to this special case. And this we will do by augmenting the HIs, by adding to each of these HIs those we go through all Z1 to Zn, then we go through successively, and for Zi or for Zj we look at all Fi's, and if Zj is an Fi but not an Hi, then we put it in addition to it. And then we show that the number of sets does not decrease by this. And then after n steps, we have our special case. That's the idea of the proof. Okay, questions so far? Then let me make a, or no questions? Should wait a little bit. I think there are no questions. So let me make a 5 minutes break for cleaning the blackboard. I have now 10:37 on my log, so we go on at 10:42.
In the Terminplaner for the oral exams, there is no possibility to make a maybe. It's just yes or no. Only 2 options.
Sorry for that. And maybe just make them yes or no.
Okay.
Maybe it would be better.
Yeah.
Because, or maybe make it these 2 yes. Recommend. Maybe 3. Yeah. I didn't fill it in myself. But I think I cannot change it now. Yeah. It's a little bit. Or maybe I can ask for a new thing, and then you can fill in this U already. then let's go on with the proof. I just got a hint that in the poll which I started, there is unfortunately no option maybe. There's just possible or not possible. So maybe just mark a few of the dates as possible. Maybe use a few different weeks if possible to make it. But that should work too. And if all days oh, I know if you give now many possible dates, then somehow the dates are blocked. But I won't block them for long because after Wednesday I will be quick to make a list that I suggest to option. Sorry for that. Okay, in the remainder of the proof, we reduce the general case to the special case. Proof. Reduce. General case. Special case. And therefore I successively will add Z1, Z2, Z3, Z4 and so on to HI in such a way that I finally get HI equal to Fi. How to do this? Well, we start with Z1. I define it HI prime, that's HI, where I add Z1, but only if Z1 is in Fi. So therefore I intersect with Fi. And I make this for H equal 1 to K. And then I define a new set, C1, just as C0, only with HI prime instead of HI. C subset of Z1 to Zn. C, sorry, forgot it. No. Fi intersected with C. Is not equal to HI prime. And we will show, and that's the main challenge to show. Let's call it star. The cardinality of C0 is less than the cardinality of C1. And this implies the assertion because we will proceed in the same way with C2, C3, C4, and so on. We will produce n different sets calligraphic C1 to Cn. And in the final case of Cn, we will have added all the Z1 to Zn, which are in HI, not in HI, but in Fi to HI, and then you will be in this special case. Proceeding then in the same way. Z2, Z3, Zn. Yields. We have cardinality of C2, C1 is less than cardinality of C2, less than cardinality of C2, and so on to cardinality of Cn. special case can be applied, and we will have our assertion. So it's obvious to show star. Okay? Okay, I changed HI by adding Z1 in case that it's in F1, in Fi, but not in HI. And then with this new set, I define in the same way this set, call it C1. I do this the same for Z2, Z3, Z4. I show for the first one that by augmenting this HIs in that way, the cardinality of the C0 increases. Then with the same proof, the cardinality of C1 increases and so on. And you, after n steps, you get a set where you are in a special case, and then the theorem is proven. Okay. So it remains to prove star. To prove star, I show that the set difference between, or the cardinality of the set difference between C0 and C1 is less equal than the cardinality of the set difference between C1 and C2. Star is implied by star. That's you look at the set difference between C0 and C1, and the set difference between C1 and C0, and then you see the C0 is C0 intersected with C1, and then the union with C0 and the set difference of C1. So these are the number of elements which you get, and the C1 is the union of C1 and C0, and the set difference between C1 and C0. So you see these are the number of. So for getting from, if you want to get from C0 to C1, then you have to skip so many elements and add so many elements. And if this number is at least as large as the other one, then the number increases. But observe, of course, this is not the same assertion as that C0, the set difference between C0 and C1, is a subset of the set difference between C1 and C0. That's not what I show. That would be a stronger claim. Okay, how can I show that one set has less than or equal to many elements than another set? Well, I just define a one-to-one mapping between the two sets. One-to-one mapping means that each element, you have a mapping, so each element of one set is mapped into an element of another set. And one-to-one means that if I look at one element in the second set, which is in the image of this mapping, then there's only one element of the first set which maps to it. To show star-star, I present a mapping from C1 to C0 to C1, Z difference between C0 to 1, in the Z difference between C1 and C0, I have to tell you what I do with the Z. My Z's are all times C. And what I do with the ZC is I just skip Z1. C without Z1. I show that this is a mapping, so it's well defined, and it's one-to-one. Well, the one-to-one, maybe make a picture that it's clear. What is a mapping? Mapping means you go from somewhere here. And if it's one-to-one, then I cannot go from one point to a point where I've already one arrow which ends with something like this. And then there must be here in this set as many points as you have points here, because with each point here will end in different point on the other side. Okay. So we are down to a. So this would be a western, and it would be now a showdown here. Now we're singing and maybe shooting and maybe 3 bullets fired here. We have to show well defined. We have to show if C is in Z difference between C1 and C0 and C1, then it's in then C without Z1 is in Z1, and if Z is in this, then it's not C without C1 is not in C0. So it's 3 claims basically. And the most simple thing is to see the one-to-one. Okay. But how to see it? Okay, what I do is I will show that if the set C is in the Z difference between C0 and C1, then always Z1 will be in that set. So assume C element C0 without C1. What does this mean? Well, C is in C0, you see this implies the condition of C0 is satisfied, so Fi intersected with C is not equal to Hi for all I equal 1 to k. And C is not in C1, which means it's not in there. So for some I0, we have an equality here. You have Fi0 intersected with C is equal to Hi0. And now you have to Hi0 prime. sorry. And now you have to look at the definition of hi0 prime. We use this definition. It's hi. Oh, very immediately I can conclude. Obviously, this implies that the hi0 prime is not equal to the hr. Or the hi is not equal to the hi0 prime. When we look at the definition of hi0 prime, that's hi. We add z1 and we intersect with fr. Now you see, if hi0 prime is not the same as hi0, the only element where it can be different is z1. So z1 must be in hi, and z1 is not in hi, yeah? And z1 is in hi prime. Does this help me? Yes. Yes. Okay, and which part of it I think help me does that z1 is in hi prime, yeah? Because this implies that z1 is in Z. So this implies z1 is in hi0 prime. This implies z1 is in Z. And now we are done with the first case because we are skipping the point z1 from sets, but only from sets which contain already z1. That's a one-to-one map. Because if two images are equal, so if C1 without Z1 is equal to C2 without Z1, and you know that both of these sets, C1 and C2, contains C1, then C1 is equal to C2. That's clear. Okay. So first part was successful. Implies that F is one-to-one, provided it's well defined. First part. Okay, questions? Any questions at that point? Well, now comes two more technical steps. So what do I have to show now? it remains to show if C is in, it remains to show C element calligraphic C0 and the set difference is calligraphic C1 implies C ohne, C without Z1 is an element of C1, C0. So let C element is 0. Okay, what do we know? Any idea about this? So of course we have the same as here, yeah? You have this guy, you have this guy. You can conclude. And what do you want to show? Oh, you have an idea?
So we know that in C, Z1 has to be in it.
Yeah, we know already that one is in Z, correct?
So if
We know all what we know all what we have written here. Yeah?
That's what we say C is in C0 and not in C0 without C1. That's important for Z1 and C.
Oh yeah, that's correct. I made a mistake here. Of course, I should start with. Sorry for that. But now it's correct. Okay, so we know this guy. Yeah?
yes, and we know that we have found Fi0 intersected with C is equal to Hi0 prime,
Good point.
and Hi0 prime differs from Hi only in the case since in
In Z1,
Hi0
yeah.
prime is Z1 and Hi0 is not.
So what you want to claim is that Fi0 intersected with C without Z1 is equal to Hi0.
Yes.
Yeah, good point, good point, good point. Okay, but maybe if I make it more systematically, then I would write this one and this one again as conditions. So the first point is we have Fi, let me repeat this again, C is not equal Hi for all I. And the second one has exists I0, you want to claim such that Fi0 intersected with C is equal to Hi0 prime. And that was Hi, the union with Z1 intersected with And now you want to conclude, and your conclusion was correct. You want to conclude that Fi0 intersected with C without C1 is equal to Hi0.
Because if we now
Maybe I just wonder how I can see it most. Fi0 intersected with C without Z1. That's it. Of course, you can first make the intersection and then skip Z1. And that's, by definition, our Hi0 prime without Z1. And if we look at Hi0 prime without Z1, that's Hi union with Z1 intersected with Fi0 and then without Z1. Oh, it's Hi0 here. Also here it's Z0. Sorry. So we're here. And now the claim is to see that what we just did with this whole operation here was we added Z1 if it's not in. Otherwise we did not change the set at all. So if Hi contains Zi, then Hi is equal to Hi prime. Doesn't help me. But okay, but we know already that we are in the special case where Hi0 is not equal to Hi0 prime. Yeah? So the Hi0 does not contain. Yeah, that's basically what we can do. We can. Otherwise, it's a little bit more complicated. This is the intersection of these two sets and the union with these two sets. So it's H0, Fi0, and the union of Z1, Fi0, and then it's now Z1. And now we know that Hi0 is a subset of Fi0 by definition. Because these were all subsets of cardinality VA plus 1, and in each one we found some subset Hi, which was not picked out yet. So this one is since Hi0 is a subset of, or Hi more general is a subset of Fi by construction. We see this is Hi0. And then you see this Hi0. Yeah, make it kind of more complicated. Now you see that that's Hi0 without Z1. and the other one union with Z1 without Z1 is empty Z. And now, since we know that hi0 prime is not the same as hi0, because fi0 intersected with C is just hi0 and is not equal to hi0, and that's equal to hi0 prime. You know hi0 prime is not equal to hi0. And then you know this can be only the case if Z1 is not in hi0. Which in the case Z1 is not in hi0. So then we see this is hi0. And from this we got that our first claim that C is in, no, it's not in, no, we get that C without C, C1. Is not in C0. Okay. First half of it. I guess the formulas are a little too complicated. Maybe, but should be clear what we did. Okay? So let me clean this part of the blackboard. Now, what remains to show? It remains to show that our special set C, where we skip Z1, that's in C1. And what does this mean? Well, we need definition of, we need Fi intersect with the Z. Is not equal to hi prime. For all that suffices to show you. And I have 4 minutes. And I think I see light at the end of the tunnel. You see too?
I know how to do this. I know how to do this.
Okay, then please.
So we can make a case distinction. So
We make a case distinction, and
we fix any I and then we do case distinction.
yeah.
Yes. And then we can say either Z1 is in Fi or it's not.
So if Z1 is in Z1 element Fi,
Then it is also in Hi prime by construction of Hi prime. And then the sets can't be equal because C without.
then Hi prime, then Z1 element Hi prime. Because it was our construction here. If you look at Hi prime, it's here. I add Z1, and then I intersect with F1, Fi. So if Z1 is in Fi, then it's in Hi prime. But of course, if you look at the right-hand side, it's not in here. Not element Fi intersected with C is not Z1. Okay. Then the second case, if Zi is not in Fi, and you have again an idea?
Yes, we can again use the construction to say that it is also not in Hi prime.
Then Z1 is not in Hi prime.
So Hi prime is Hi, and then it follows from
So
C being in C0.
Hi prime is equal to Hi. And then it follows from,
Because C was chosen to be from C0.
and so you look at the left hand side, Fi intersected with C without Z1. Since we know that now Zi, no, it's a Z1 here, sorry. Z1 is not in Fi prime, then I don't have to skip it from C here. So that's the same as Fi intersected with C. And if I intersected with C is not equal to Hi. And Hi was equal to Hi prime. And what we used here is, here I use Z1 is not an Fi1, Fi. And here we use that C is in C0, yeah? And then we are finished. Okay, if you don't get all the details, then look at again at the lecture notes. It's a little bit complicated proof. This proof won't be on the list of exam questions. I think this is a proof which basically can prove it without looking at my lecture notes, but I don't want to prove it without in my lecture notes. Okay, any questions? So then I'm done for the day and see you again on Monday.